Hello everyone. And today, because Professor Han is out of town, so we two TAs will give the lecture. Actually, we're not giving the lecture. So today is a survey presentation, and also the next lecture, like next Tuesday, will also be the survey presentation. We have read all of your surveys. It's pretty good, but we still need to select like 8 of them as a good surveys. So we will ask these 8 groups to show their survey paper and in these 2 classes. So today we have 4 groups to present their surveys, and every group will have 15 minutes. It seems not working. After 15 minutes, they will take questions. So just keep the time under control. I will just set alarm for every group. All right, let's get started. So the first group is John, Henry, and Xin Lu. Is the group already here? Okay, yeah, sure.
Hi, everybody. My name is John, and this is Henry. Our third partner is not here, so hopefully she shows up, or I could cover for her in case. So anyways, our research topic is in clustering time series. So if you recall, a few lectures back, we covered spatial temporal mining, and there was this really nice diagram and how we talked about the integration of all 4 of these aspects led to some interesting research. So we kind of wanted this to take a look at just one portion of this entire diagram, which is the temporal data, so time series analysis. So, I mean, time series is pretty much ubiquitous with, in terms of any applications, right? So you have financial time series, you have environmental sensors. Anything with sensors really collect data in terms of time series. And so this is why we pick time series. Another important reason is that we pick clustering in particular and not classification or any other mining task is that time series clustering was often used for more complex data mining tasks, such as rule discovery, indexing, and classification and anomaly detection. And so that's why we settled on clustering in particular. Okay. So, I mean, a time series is probably pretty much obvious. So you could think of it as a tuple or just an array with an ordered array. So it's just observation collected in sequences. And it could be one-dimensional or two-dimensional. We'll focus on the one-dimensional because most of the algorithms or the stuff we talk about is applicable for multidimensional as well. So some of the challenges that a lot of research face in terms of this is that time series data are very, very large, and so there's usually stored on disks. So there's been a movement for analyzing streaming data now. And so, but there's still a lot of work that does with stored data. It could be high-dimensional, as discussed, and so a lot of the papers and algorithms try to take this into account. And the data is often noisy and has outliers and shifts, and so it might screw up a lot of the similarity measures that you might be familiar with. We'll talk about that as we get along. And so there's 3 types of time series clustering, right? So there's subsequence clustering where you have one time series, you segment it, and you try to form clusters of the subsequences. There's whole clustering in which you have an entire data set of different time series, and you try to cluster those time series together. And then there's also time point time series, which is essentially the same thing as segmentation. So you just consider the temporal part of the time series and not the data itself. For our project, each of these itself could be a research area. So we'll focus on whole clustering. So as mentioned, time series are often high dimensional, and a lot of work is done in terms of dimensionality reduction, which in this case we call it representation. So how to represent a time series for you to be able to do any mining tasks on it. And so this is a big part of the literature. Representation schemes are usually split into 4 different groups: non-data adaptive, data adaptive, model-based, data dictated, and I'll go through briefly each of these and then discuss the most popular ones that are used. So non-data adaptive only consider the local properties of the data. This is commonly used in any signal processing papers or applications that you see. So you could look at the time series in the frequency domain instead of the time domain. You could do a wavelet transform, random projections. So these type of representation, as stated, only considered local properties such as the mean of the time series. Most commonly used one is PAA. And so PAA is essentially you're just dividing the time series into segments of equal size and compute the mean. And that will be your representation, right? And then here you can specify M for whatever you want to be. Okay. So these are pretty straightforward, pretty simple. Most of this discrete wavelet transform is computed in linear time. So data adaptive representation tries to take into account the entire time series and try to minimize global reconstruction error. You might be familiar with SVD and PCA. There's more recent ones. The most popular of this is symbolic aggregate and then shapelets, which is based on SACS. SACS is interesting, and it's the key area of our research project, and it's probably the most popular one. So SACS is essentially converting a time series into a string that you could analyze. So SACS first, here's an example. So SACS first does the PAA that from the previous figure on the time series. So it splits it into M intervals and compute the means, and then it normalizes that interval, each of the results from PAA, and then it assumes that after you normalize it, you have a standard Gaussian, and it splits the standard Gaussian into equal probable regions, which it calls breakpoints. And then it assigns a symbol to each of the PAA discretization results based on where it lies in the breakpoints. So like I said, for example, so here you have the time series, you split it up, and then you have the breakpoints, and then you essentially convert this time series into a string. So it's probably the only representation that does this, and so it's the most popular one. And so because it enables you to use stuff that you will find in text mining, in doing mining tasks on time series. So SACS is also, you could also convert a time series to SACS in linear time. So it's quite popular. This is really new. Shapelets are essentially, it's built on SACS. It's actually from the same research group. It's essentially determining the subsequence of a time series that best represents the time series using entropy, so stuff from information theory. I'm not going to go too much into detail about it due to time, but you essentially know what it does. Okay, model-based representation, the third one, is stuff you would commonly find in the statistical papers. So hidden Markov model, ARMA, and this is pretty interesting also, which is bitmaps. But reading that is bitmaps are essentially SACS with 2 symbols. So bitmaps is essentially converting a time series into sequences of zeros and ones. So SACS converted. So if you set SACS with 2 symbols, it's essentially the same thing. Data dictated representation is different from the other 3 representation methods that I mentioned, and that it requires no user input. You're not trying to minimize reconstruction error. The only notable example I found of this was the clip representation. So, okay. So next, we'll talk about the distance measures. Here, as you can see, whatever representation methods you use will determine whatever distance measure you use, right? So if you use a Sachs representation, you could use stuff like edit distance that's commonly used in text mining and stuff. Whereas that won't work for any of the other representation. So we all probably know the benefits of or some of the properties of some distance measures. Not all distance measures have these properties, and the benefits really depends on the underlying problems, right? So you could prove something that is essentially you just have to prove something is a distance measure, and whether it fits the triangle inequality and whether that's helpful for you or not, it depends on the problem. But the most useful property is the lower bounding property, in that your distance measure provides a lower bound. I think I had it screws up. Had the symbol the other way around. But anyways, your distance measure provides a lower bound for the Euclidean distance, because for time series, lower bounding is a measure which needs to, so whatever you compute, you try to have this lower bounding property, which is somewhat really difficult to prove. But it's a nice property to have, because the Euclidean, if you do the Euclidean on the raw time series, that's usually one of the most accurate. So if you have a lower bound of that, it's better. Anyways, so distance measure for time series, as stated, depends on the representation you choose, the application, and it's algorithm specific. So you have something like dynamic time warping, and if you use that with k-means, it doesn't guarantee convergence in k-means. It often does not converge. So you wouldn't use DTW with k-means. You would use it for something else, right? And as mentioned, Sachs allow you to use distance measure from text mining, or you could borrow stuff from BioInfo. For time series in particular, there's 3 types of distance measure: time-based, shape-based, and structure-based. And they're probably all self-explanatory. Time-based focuses on the time observation that occurs. So it's essentially you have, for something like the Pearson, where you just look at the correlation between the fixed intervals, right? Which is very inefficient. You could also use Euclidean, where if you just consider the time instead of the observation. Shape-based is the most commonly used. You use the Euclidean on the observations, or use irregular time warping, and then there's something called min-dis for Sachs. So you're essentially looking at the shape instead of the time. Okay. Everybody's familiar with the Euclidean, and so this is how it looks like when you compute it for the time series, right? So you have 2 time series, and you just compute the distance between the observations. So that's pretty straightforward. The thing is, the Euclidean sometimes does not give you good results if the time series is irregular. So imagine if you have this thing shifted, right? That would not really give you an accurate result. So that's why there's something called dynamic time warping, which is essentially trying to find the minimal distance between this point and a group of intervals, or a group of time intervals in the time series. This is commonly used, and the only problem with it is that it's very slow, but there's been ways that's recently been developed to how to compute it faster. Okay. Structured base is usually for the statistical representation that I've mentioned. It's really based on the parameters or the model that you choose. So for ARMA, you would use the autocorrelation function. For hidden Markov model, the model itself already captures the dependency, so you don't really use anything. And then, so like I said, we focus on the Sachs representation because that's the part of our research, and it's the most common. So for Sachs, you could use the edit distance, which determines, you could just do a cost of 1 for insertion, deletion, or substitution. But everybody knows that using the edit distance might be somewhat very slow. Because if you imagine you have your really, really long Sachs string, right? And it has large numbers of symbols, which could be anything. Computing the edit distance of that will take forever. Okay. All right. So min distance is another distance that's used for the Sachs representation. It's based on the Euclidean, and it's a lookup table type of method. What's interesting about this is min distance provides a lower bound. So this is commonly used. There's also another thing called fast SACs, and then an extended edit distance, which tries to compute the edit distance, but also take into account the frequencies of the symbols as well. Yeah, so anyways, we don't use any of that. We propose our own similarity measure based on stuff found in bioinformatics for DNA sequence alignment. So that's the scope of our project. So, okay, that's all for distance, and then you take over the clustering of how much time we have left.
Okay, so I will talk about the clustering algorithms. So there's a different base time series clustering algorithms that I don't have time. So there's a partitioning, grid-based, model-based, density-based, and multi-step clustering. So partitioning based is basically like k-means, which minimizes the total distance between all items in a cluster to the cluster center. And there's also a soft clustering version that has a probability distribution of each data point belonging to each cluster. Wait. Oh, God.
I think you go back to the main diagram at the beginning. Yeah.
Okay. So a drawback of partitioning is that clusters that produce are as compact as possible. So you might not get, so if there's a huge cluster, you might break that cluster up into two clusters so that you get a smaller distance measure for each cluster. And the strength of hierarchical clustering is that it produces an ordering, so you can actually visualize the result of your clustering algorithm. So here you can see that we use hierarchical clustering to cluster, to kind of evaluate different distance measure, and we know that SACS performs better just by looking at the diagram.
The takeaway key is that for clustering time series, they're going to use partitioning or hierarchy. So
Yeah.
that's essentially it.
So as your project, I saw that you want to cluster the sequence in biometrics. So what kind of methods are you using in your project? What kind of clustering exercise?
So we base our method on, I cited a modified DMK. So DMK essentially takes into position the sequence frequency, position, and it's relative like occurrence, tuple occurrence. It's commonly used in bioinformatics, but the problem with it is that in bioinfo, especially for DNA, it's base 4. So we have the 4 nucleotide base. And so we modify that to work with essentially N symbol. And we found that it provides better results than SACS, using for SACS than the other representation scheme.
Okay. As for the clustering results, sorry, the clustering algorithm, what do you think is the best? What is the best that will work best together?
I say hierarchical because it's very applicable to this problem. But
And you can use different distance measures.
Very, very nice.
The next group is 门区一只猪瑞焦。弄个钉，直接弄个钉。OK。
Hi, good morning, everyone. Today we are going to talk about the neural network language models. And I'm Ray. This is Meng, and he is Yizhi. So firstly, I'm going to talk about something about the statistical language models. It aims to learn the distribution, the probability distribution among the sequence of the words, and it's very widely used in the natural language processing task. For example, just like the machine translation, information retrieval, and speech recognition. For example, in the speech recognition, it's used to distinguish between the words and the phrases that they sound similar. And among the statistical language models, the n-gram language model is the most commonly used, and is used to predict the next word based on the previous words. So if given a word sequence based on the nth order Markov assumption, we can predict the word sequence based on the formula. And we assume that the probability of the word we're going to predict is only related to the previous n words. In the parameter estimation part, we can use the maximum likelihood estimation, and also we can use the conditional probability that can calculate from the n-gram model frequency counts. And although the n-gram language model is commonly used and is simple and efficient, it also has some problems. For example, it has too many parameters. And when the n goes large, some of the n-grams will not be observed in the data. And because we assume that all the words are independent, but actually some of the words may have the similar semantic meanings. So how to solve these problems? Next, my team member gonna give some introduction.
So thanks. So to solve this problem, a very novel neural network language model is proposed in 2003. So which solves these problems to a large extent. So basically, the idea of the neural network language model can be summarized into three aspects. Please. So sorry. So firstly, the neural network language model will associate each word in the vocabulary with a distributed real-value vector representation, or you can call this representation as word embedding. So the similar words will have similar representation. Which is shown in the picture. And also, the neural network language model will express the joint probability function of the word sequences in terms of the feature vectors of these words in the sequence. For example, here we already have a diagram show me, and we want to predict the next word, your. So in the neural network language model, we will first use the embedding vector of show and me to represent the history diagram information. So here we can simply concatenate the embedding vector of show and me to represent the history, or we can take average of the two embedding vectors as a history representation. So after that, we will send the history representation to a multi-layer neural network, and we will use here we will use a softmax unit to compute and to normalize the output to compute the probability distribution. So by doing that, the neural network language model will have great generalization abilities. So consider the two sentences here. So in the n-gram model, the two sentences will be regarded as two independent ones. But even though they have very similar meaning, but in the neural network language model, as the and will have very similar embedding. Cat, dog will have very similar embedding. And because the probability function is a smooth function of the history vector representation, so that the neural network language model are able to realize that the two sentences are very similar, so which solves the sparsity problem. So, and thirdly, the neural network language models will learn the word feature vectors, and the parameter of the probability functions simultaneously by using the backpropagation algorithm. So first, we can compute the error of the output layer, and then we can backpropagate the error to the fully connected layers and to update the parameters. And finally, we can backpropagate the error to the vector representation to update the word embeddings. After that, I will introduce several famous neural network language models. So the first one is the feed-forward neural network language model. So the structure is shown in the right figure. So this model has 3 layers. The first layer is the input layer, so which is the representation of the history. Here, the model concatenates all the vector representations of the previous n words. And after that, the information is sent to a hidden layer, and the information in the hidden layer is then sent into an output layer, and a softmax unit is used to normalize the output. So for the optimization algorithm, the backpropagation and SGD algorithms are used. And then a log bilinear language model is proposed after that. So the only difference is of the log bilinear model and the FNN language model is that the log bilinear model uses a bilinear function to compute the score of each word. And the advantages are that the log bilinear model will have less parameters, so it is more efficient. So the previous models are still based on the nth order Markov assumption, so which use the previous n words to represent the history. But sometimes we need longer history, and so we want to use all of this history word to compute the next word. So Rn is based on this hypothesis. So ideally, it is able to use all previous words to represent the history. So the structure of Rn model is like this. So here we will use the ST vector to represent the current history. So in each step, the current history is computed according to the previous history and the current word. And after that, the probability of the next word is computed according to the current history, just like that. So for the optimization, the backpropagation through time is used. So the basic idea of backpropagation through time is to unfold the recurrent layers into multiple layers, so that we can train the Rn model just like to train deep neural networks. So the Rn is able to use all of these history words, so which achieves very impressive results on the language model task.
So ideally, the recurrent model mentioned before, we use all the previous words into the computation. But in the real case, like only the previous several words can be used, so that the context-dependent recurrent language model is introduced here. It explicitly computes the search history into a context vector, so that this model can provide this context vector as an additional feature and to the neural network training. And as we can
as described above, below, this model uses LDA, which is the latent direct allocation, to infer the topic assignments of each word. And we use the previous 50 words as a global context representation. In other words, it's just a search history. So let's see some computational details. Similar to the variables before, ST is the hidden layer, WT is the include layer, YT is the output layer, and FT is the additional feature we introduced. It should contain some contemporary information about the current word WT, and that contemporary information can be any source information, such as like part of speech lags and morphological information about the current word, and etc. So as we can see, the FT connect directly to the hidden layer ST and also the upper layer YT. And the computation formula is here. The training of the neural network is to find the weight matrix U, W, F, V, and G to maximize the likelihood of the neural network, the training data. So, and the change function here can be replaced by the sigmund function as well, and the G function is the softmax activation function, similar to the recurrent language model as well. So that's about the context-dependent language model. And here's the experimental result of all the model we mentioned today. So the general rule is that the perplexity is smaller, then the result is better. So let's see, this part is the n-gram performance, and which is generally worse than the models we introduced today. So from log bilinear to feed-forward and to the recurrent neural network model. So we can see that the recurrent neural network model gets the best performance. Like its perplexity is always the minimum in most of the case. Some brief conclusions. So statistical language model is critical, and the traditional n-gram model has some severe problems. And today in our survey, we introduced some like very new models, which are especially for the recurrent language model, is very effective and promising in practice. Thank you.
So next group is 说招时期.
So hello everyone. So today our group topic is embedding method for word and text. Our topic maybe have some. Hello. Our topic maybe has some small overlap with previous group, but it's okay. When we have some overlap, I will try to omit that part. So here's our today presentation outline. So the presentation will be mainly about two parts. The first is original word embedding or word representation, which will talk about the original idea of word embedding and how to apply this original idea to different related domain, including knowledge graph and network embedding. So in this part, we'll mainly see like how to embed, what to embed, and why the word embedding, this kind of idea is is successful. So in the second part, we will talk about like how to extend our extend the existing word embedding to text embedding. So we will talk about several methods here. So first, in the first part, we will talk about the original word embedding. We will introduce several models, including skipgram, continuous backup words like implicit maximum matrix factorization, GLOVE, and we conclude with an experimental paper called "How to Generate Good Embedding." So the first two most initial model is like skipgram and the continuous backup words. These two models are based on kind of called distributed hypothesis, which is like words that with similar context should have similar meaning. Like if two words apple and pear, so we can talk about I eat an apple during lunch, or I eat a pear during lunch. So you can see that the word around apple and pear are similar. So in this hypothesis, we think like if the words around the target words are similar, so therefore these two words should have like similar semantic meaning. So let's talk about these two models. We can see two models are quite similar. For the CWOB, like continuous backup words, so its object function try to use the context word, is word around target word, to predict the target word itself. But for the skipgram model, its object function try to use the target word to predict the word around, which is the content word. Actually, you can see if we put this two graph illustration of model here, you can see they are quite mirrored. So doing their model, so although some people call they are like neural network based, but actually it's quite a linear model. So what they do is try to use softmax our function to do the prediction, but we can clearly see there's some problem with the softmax function. So you can see when we try to compute the softmax function, we need to sum all the vocabulary from W from 1 to W from W. So when the size of the vocabulary of the words is very large, usually like 1 million or 1 billion, this will take a lot of computational time. So in that paper, what you've had, the author introduced two methods to solve this problem. The first is called negative sampling. So instead of calculating the softmax function we have shown here, so the author try to approximate it with one positive prediction and k negative prediction. So each prediction was formulated by the sigmoid function. So positive function is replaced with sigmoid function, and negative prediction is replaced by one minus the sigmoid function. So instead of calculating the size of vocabulary, now we only need to calculate 1 plus k sigmoid function. So the second kind of approximation is called the hierarchical softmax. So basically it is like try to approximate with a tree structure. So author has built a tree, and in this tree, all the leaf nodes are the word. So in order to obtain the probability of a certain word, so author will go from the root and find a path to the leaf. So during the path, each node has associated with a sigmoid function. So to calculate the probability of this root, this leaf, it will multiply all the sigmoid function along this path. So this is a binary tree. So if the tree is on the left, it's times sigmoid. If on the right, it's times 1 minus sigmoid. So for this hierarchical softmax, now author need only to use log W instead of log kind of computation. So actually, in real, like people like more likely to use like negative sampling. The reason is first, like negative sampling is much easier to implement. So instead of hierarchical softmax, you need to build a tree which are more complicated. And also, like the results, the performance of negative sampling and the hierarchical softmax are quite, it's almost similar. Maybe native sampling has even like 1 or 2% better performance than the hierarchical softness. The third reason is there are some people have tell people about what's really the native sampling is doing. So she has a paper like maybe 2 or 3 years ago that's called implicit regarding the word embedding as implicit matrix factorization. So one kind of contribution in this paper, so it is try to provide explanation for skip-gram model with negative sampling. So what the author in this paper does is that they try to reformulate the object function in the skip-gram model with negative sampling with some variable that is very common to author, like the number of times that the word appear in the document or number of times that the word pair appear in the document. So with some simple math and to the end they get some very simple result which tells people about what's the what2vet algorithm are really doing. So we can see like on the equation 9 is the result. So what's the what2vet this algorithm really doing is if we dot product the word-vet and the content-vet in there, you get from the what2vet algorithm, it's really a biased pointwise mutual information. So pointwise mutual information is something widely used to define the similarity of word in information retrieval. So now we know like so what's the what2vet algorithm really want to embed is some kind of static information you can find in the document. So it uses a quite matrix factorization, which is a kind of linear model to do this. But the good things of what2vet because is that with native sampling you can do it very efficiently and doing a parallel model, so which is much faster and easy when you do matrix factorization, because for matrix factorization you probably need to put the whole document or word matrix into the memory, which is pretty large, so people cannot always do it. So then come to the next model. Next model is called Glove. Maybe I will go through this very fast. So it's quite similar to the what2vet algorithm, but the design idea is quite different. So for this Glove paper, so author is doing some from so their first principle is try to embed the word static, like the co-occurrence of word pair in the document, try to embed this kind of information into kind of latent embedding continuous vector. So with this first principle and some probability needed for the word embedding, so the author designed this Glove algorithm. So we have seen that a lot of word embedding algorithm now. So there's also a very interesting paper last summer. It's called How to Generate Good Word Embedding. So you see from 2030 to maybe last summer, there are a lot of number of word embedding algorithm, but actually people are not very clear what kind of things can help us to have good word embedding representation. So in this paper, the contribution of these authors is that they have done a lot of experiments to show how to generate a good word embedding for different kind of application. So there are results is shown here. So the first thing is they find out that faster or simpler model, just what2vet, this kind of linear model, was sufficient in most cases. And also the large number of documents input data can improve the quality of word embedding, but at the same time, the domain or the quality of the documents is more important than size. And also, another thing to think about is when to stop training the embedding model. So they also found out the cross-validation losses maybe are not good matrix for stopping. Maybe it's better to check the performance of the final application of your task than the cross-validation of just the word embedding. So the last is talk about the dimension of the word embedding. So the larger dimension can provide better result in general, but the problem is like larger dimension usually cause high computation. So in reality, like only 50 dimension is really enough for kind of basic task. Then we come to the next step. We will see like how the idea of word embedding like used to other related domain. The first domain is a knowledge graph completion. So in this part we will see about the question about how to embed. Okay. I'll speak. So the knowledge graph is try to kind of embed this kind of triplets, the head, relationship, and tail. So like head maybe me, so child relationship maybe is the student of, and T maybe UIC. So it tried to embed this kind of knowledge graph into the continuous vector space. So this idea comes from kind of popular property of word-to-vet is kind of analog properties. That is, vector of king minus vector of men plus vector of women is approximately equal to the vector of queen. So since some kind of researcher tried to think about this kind of models that embed this vector of head plus vector of relationship equal to vector of tail, but for this model called transaction E. But the problem with this model is like if we have many to one or one to many or many to many property, this model will not work. So there's another model called transaction H, which we for each relationship, we have hyperplane which do this kind of projection. And we also, they also have the translation R. For each relationship, there's a new like space, which translation use kind of a positive semi-definite matrix, which for each relationship, you can translate some into a new space and do this kind of embedding. So we can see that in this community, people try to use different kind of operation in the vector space to try to embed a different kind of relationship. So the third part is called network embedding. In this part, people are more focused on what to embed. So they try to design different kind of similarity to embed. Like in word events, the people try to embed is the co-occurrence of word pair, but in this network embedding, people try to define what's the similarity among the network they try to embed. But they are using the basic ski-gram model, which is we introduced at the very beginning. There's a deep working line. So actually, these two ideas are quite similar, but the difference is how to define similarity. So there's something missing just to talk about. So in this community, people try to focus on what to embed, but I don't know why, but they not focus on what to embed. But from our previous knowledge graph completion, we can see there's a lot of idea we can bring from that community. So at least we can, it's worth to try. So for last part let's talk about the text representation. So text representation is try to extend the word embedding to text. So the most straightforward model is the dot-to-vet model. So it is a straightforward extension of continuous bag of words model. So instead of input is kind of content among the target words, it's also plus additional vector for text. So training similarly. And there's another paper which is very interesting, like try to get the distance for two texts just with a word embedding. So one contribution of this paper is proves that the average, like a common like text embedding we use is average word embedding is kind of a lower bound for the distance they choose. So it's give us explanation so why the average word embedding is kind of useful in reality. So the last one is kind of a ski-gram model called skip sort. It's kind of using like a recurrent neural network to try to composite word into text. But they still they use kind of ski-gram model, but combined with recurrent neural long short-term memory. So it's quite of interesting. So our project will be extend this model. So this is a conclusion, and thanks for attention.
So you need to construct the network based on the similarity. So
Yeah, actually. So I think that's the reason why a lot of people try to design smart way to define the similarity in the network.
And also for the representation of the knowledge base, to represent the relationship in the knowledge graph. So actually, sometimes it's hard to explain why the like the subtraction between two vectors can represent this relationship. I don't know if in the paper they they do they make some like adjustment some
Yes,
calculation on that?
they will like split the knowledge graph into text and validation, and so if the validation like the error is low, so it means yeah.
I have one more question.
Okay.
So, so you know that usually when we change like word to that,
Yeah.
or this word embedding a very large data set,
Yeah.
Wikipedia data.
Yeah.
But we know that words have this semantic drift, that they might have different meanings in the
Yeah.
specific domain.
Yeah.
So it might be, not correct to use the embedding chain from the large corpus. How to deal with that?
Yeah, so there are people like try to like there's a similar word, but bank is maybe a river, maybe just a bank like the PNC or Chase. So it's first annotates the word with different meaning, so with some kind of mechanism in natural language processing, and then the same word with different label with regard as different word during the training. So there's a kind of solution for this, but probably we can use more smart way to solve this problem.
I have another question for the network embedding.
Okay.
So basically, how you generate the network is really depends on what the task, what the target of your, what the object, what the target of your task. So
Yeah.
if it's the classification task, this generation may be different from the representation task.
Yeah.
So does any paper mention this kind of?
No, actually, like you can see, the people on like network embedding research is quite limited. There's only like these two papers are most famous until like last 2 years. So recently, there's people not like they're all focused on general question, not on the specific question about what kind of task it is. Yeah, but actually, yeah, just really the task you are doing is really like what decides the performance of your embedding. Like in our like presentations as a paper about how to generate good word representation, in this paper, people always say like the task is more important than the cross validation because. Yeah. Thank you very much.
Do you regard the language model as a frame of network, word-to-word network?
Yeah. Some people try to do it. So you use heterogeneous information networks. There's kind of a lot of information you can regard like word to word, word to dot. But the idea is quite like train several type of word to vet and conjugate them.
Right.
Yeah.
And as you mentioned that for learning neural language model, you could write it as a matrix algorithm.
Yeah.
For line or deep walk method, and I think probably it could be written as a kind of matrix algorithm.
Yeah. If just using they didn't mention, but I think if you do some little math, you can find there's a kind of there's equivalent to a kind of matrix factorization because what kind of methods they use is quite similar to the word to vet. Yeah, thank you.
Actually, even for heterogeneous networks, because there are multiple types of the entities, it is actually similar to tensor factorization. So these are all equivalent in computation-wise. Cool. So we have our last group: Wendy, Paul Wei, Shen Liang. Which one? Yes.
Hello, everyone. Today we would like to introduce our survey on spatial temporal activities. Here's the outline. We would first introduce what is spatial temporal activity and why we want to study it. Then we will introduce 4 groups of models, and then we make a conclusion on our survey. So what is spatial temporal activity? We define it as activities users are likely to perform at a specific location and time. For example, UIUC students would like to eat in Green Street during weekdays. And based on whether we include an individual user's information, we could further divide those activities into 2 groups, global ones and individual ones. And why we want to study this, actually it helps to explore the geographic topic distributions, user mobility, and the topic preferences. It serves as a critical step for many other tasks like location and tweet recommendation, user profiling, and topic tracking. So in the next 4 sections, we would like to introduce 4 kinds of models based on the factors considered in the models, likely when, where, and who. So first, I would like to introduce models for spatial activity, which we only consider locations and activities and their correlations. And to make my introduction more clear, I would further divide those models into 4 subgroups based on the underlying technologies used in those models. The first one is latent Dirichlet allocation-based model. One first proposed a model called the location-aware topic model, where in this model, he introduced a latent variable for topics, and as you can see in the figure, words and locations are generated by the latent topics. And in 2010, Hao developed a location talk model based on the LATM. In his model, the authors extend LATM by introducing 2 kinds of topics instead of only 1 kind of latent topics, namely global topics and local topics. In his model, more general terms, words are grouped into global topics, while the terms related to local events go into local topics. In 2010, a latent variable model is presented. In this model, the main difference is that he introduced 2 latent variables in the generative model, namely topic and region. In the right figure, we can see that the general process is as follows. A latent region generates the geo coordinates of the documents, and the words are generated from both a latent topic and a latent region. And geofork is just the same as LATM, but in this model, location is represented as a pair of latitude and longitude instead of location ideas, which are discrete. So the second subgroup is PLSA-based model. In 2011, a latent geographic topic analysis is introduced, and in this model, there are also 2 kinds of latent variables, namely region and topic, and each latent region has a topic distribution and a bivariant Gaussian distribution over location coordinates. The generative process is like, for each document, we sample a latent region from a multinomial distribution, and then location coordinates are generated from this latent region by a Gaussian distribution. Finally, for each word, topic is generated from the latent region, and a word is generated from the topic. And the second subgroup is multi-Dirichlet process-based model, which is proposed by Klein in 2014. Instead of assuming Gaussian topic distribution, he explores non-Gaussian distributed spatial structures among topics. And we, in 2011, also applies some simple supervised methods for document geolocation prediction. He only used raw text as evidence, and in his model, geolocations are represented as discrete grids over the Earth's surface. The best strategy he found is KL divergence. The idea is very simple. He just finds the grid cell whose Bohr distribution has the smallest KL divergence from that of the text documents. The main drawback of this model is that the grid cells are predefined and cannot model very complex geographic regions. So next, Shenliang will introduce spatial temporal activity models.
Now I will introduce how to model spatial temporal activities. Qiao Mei has proposed a PLSA-based model on 2006. It assumes each word is sample. It assumes each word is sampled from a mixture model with multiple multinomial distribution as components, and each represents a theme. A theme in a text connection C is a probabilistic distribution of words characterizing a semantically coherent topic or subtopic. So in this graph, on the left top, the TL is a probability to choose this special temporal context at time t and location L to generate a theme. We call it global theme. It's from theta 1 to theta k. And in this mixture model, we classify the word into two categories. One is the non-informative word, which is the, of, and in a document. So, and another one is the informative word. That is words that we are interested in to analyze it. Correspondingly, they create two background models. One is the background model that is used to capture the common English words such as the and of. Another model is the global theme model, is to find it is used to find the informative words in all articles. So so the word is generated from the two models. One is from the background model. The number B means we choose the words from background model with a probability number B, and another property from the global theme model. And we use a EM algorithm to keep running the iteration. The word goes into the document. So until we hit the whole maximum, this model will stop. And this model shows that it can effectively extract useful information from weblogs. So, yeah. Another model is based on LDA. It simply applies a special temporal extension to LDA and detects the dominant topics in the neighborhood. It can recover the topics discussed in a city by Foursquare users, and it ranks these topics according to an intensity measure, observing that the most popular topics are similar across cities and correspond to well-known urban activities such as work, food, and nightlife. It also uses entropy-based measure to show that some topics in Foursquare are highly focused geographically, while others span larger geographic areas. So next, I will introduce Paul Wei to give an introduction to spatial temporal and.
Okay, so next, well, these works modify the models the behaviors of individual users. So that is to say that they add to the who aspect. So first, there's a very simple model in which the region is based on both the global popularity and individual users' preference. And then the same team next proposed another model which is based on nested Chinese restaurant franchise process. So here the regions are following a hierarchical tree structure. in which every region in the upper level geographically encompasses the region in lower level. And same goes with the topic that correspond to the region. So for a topic that corresponds to an upper level region, it's more diverse and it includes every subtopic in its region in a lower level. And in this model, how they generated a region is basically follow a path that goes from root and all the way to a leaf. So whenever we encounter a node in the tree structure, we do a sampling and choose which direction to go, and until we reach a leaf, a region is then finished sampling. So the above two models, they only consider the coordinates of a location. So in a region, they only use Gaussian model to generate a location. But in the third model, instead of only using coordinates, they also use the semantic information of the location. That means that they have some prior knowledge about what is this location about, what are some common topics about it. So they will consider both these factors. Okay, then next we arrive at our destination, which is to model the individual spatial temporal activity. So here, all the four aspects, who, where, when, and what, are included in this model. And this is by far the first model that involve all these four vectors. So I'll quickly go through their generative process. So first, a time factor is sampled. It includes day of the week, either a weekday or a weekend, and then the time of the day. And then a region is generated based on both user and time. So back to the example that Wenqi has mentioned. So for example, for UIUC students, if in weekday and it's daytime, you probably will be near Civil Center, and probably in lunchtime, you have a higher probability to be around Green Street. And then using this user and region, we can generate a topic. So for example, when you're near Green Street, for example, you're a grad student, whenever you're near Green Street, probably you're finding something to eat. And when you're in Civil, you're probably doing something related to your work. And having this topic and region, and then they can generate the location and words. And notice that here there's a switch to sample the trade-off between the factor of topic and factor of region. And then a year later, the same author has proposed another model, is EW4, which is an enhanced W4. And there are some modifications from the previous W4. So first, they use a non-parametric Bayesian model, means that there's no manual tuning of the parameters. All the parameters can be automatically learned from the training data. And then they use the CRP Chinese restaurant process to sample the regions. This means that for a user, they have some probability to choose from existing regions, and the probability is proportional to the popularity of this region. But with some fixed probability, they will create a new personal region. Okay, and the trade-off we just mentioned, in this EW4, there's a way that they can automatically sample it, but also learn it, so that it's not a fixed trade-off ratio between them. Okay, so to conclude, we have surveyed the existing methods of modeling these spatial temporal activities and using these geotagged social media data. And so here's our presentation. Thank you.
just focus on the technical parts. Yeah.
Because sometimes the integration they would have a big impact. So
Yeah.
like have a look at how they do the integration.
So that's all for today. And the sign up sheet is here. Oh, who doesn't sign up yet?
我不知道是你，因为是知识，你看知识他弄错了，他在这边写的是文体，我想这是谁啊？文体和，然后我就直接按照这个说。
对，这我 copy 过来的。你为什么文体？因为它有 auto 那个。哦。
它会被 auto correct，
我不知道是。
我在写。